Before we go to class today, okay, I want to talk about the milestone one project assignment that you have to submit next week. Okay, so the link on e-learning will appear to you next week, starting Sunday next week. So what you have to submit is the plagiarism declaration. Okay, the report, which is all the proof of work inside report, inside the PDF report, and then the reference, okay, together with the report. Okay, you don't have to submit the rubric, okay, because I will set the rubric in the e-learning, right? So this is the page of the plagiarism declaration where you have to split only this page from the PDF and put it together in your report. Okay, any question? Okay, make sure all team members fill in and sign. Okay, fill in and sign. So in other class, when they have like extra member, okay, they make it 2 members in the group. Okay, but I don't want a lot of group in my sections because I have a lot. So this is our grouping. So this is our grouping actually. It's just that okay, the name in the blue is the name that I put randomly. So previously, is Hassan here? I'm not sure which one is which one. Is it Ibrahim Hassan or Hassan Mustafa? Let's see. They want another one group member. So if you want to change members, so make sure you discuss properly. Okay, you discuss properly with the 2%. Like for example, if Zuhairi here and Fatin want to exchange the group, you discuss properly, and when you decided, you tell me you want to change. Then I will make the change. Okay. Same goes to Asir Sharif here and Dafa, for example. If you want to change, okay, let me know. Okay, you discuss between both of you, and then let me know the conclusion of the discussion. Then I will change, right? So I will upload this in your e-learning and later in also in the WhatsApp group. So that's the second part. Okay, this one will also be uploaded so that you know the rubric. So this one is the updated rubric, but it's just the same rubric that I discussed with you previously. It says I asked them to make it from small number to big number, and it should start with 0. Okay, because if you don't have simulation, why do you have to get 1? You have to get 0 for that. If you have missing simulation, diagrams, and analysis, and so on. Okay, and there's also some weightage. Okay, for simulation. No weightage here for hardware functionality, but that is for milestone 2 and milestone 3, right? Which means you will lose more mark if you don't if your hardware is not function properly in milestone 2 and milestone 3, right? Because the weightage is times 4 here, right? Any question?
Yes, simple question. To
Uh,
one milestone one.
Ahmad Abdullah Ahmad Al-Damashi. Maybe you're not in this. You don't have group?
No, I saw my name now.
Oh, okay. Sorry.
Thank you so much.
All right. Should I? Okay. Here again. Right. So I will share with you later. So any changes? will be discussed later. If between you. Right. So shall we proceed with our class today?
Yeah, sure, Sensei.
All right. Ikimashou. Okay. So this slide is basically revision on the Boolean algebra. You already know what is and or not, or if you can't remember, you can just refer back to digital electronic or refer back to my video. And then if you, I will eventually make a video of this, but this is not the new knowledge that you need to know. So I will not rush. I will not make a video in a rush. I will make it eventually, maybe before your test one, maybe during the semester break. Okay, I'll find some time to do it. All right. Okay, you've done this. You know what is the canonical POS, SOP, the min term, max term. Okay. All right. The what's called this? The function using the min term and max term. Right. Logic minimization. How to do logic minimization. Okay. And then the K-map. And then I realized that um, you haven't actually done the entered variable K-map, have you? For those who's taking digital electronic in UTM.
No, doctor. First time I hear it.
No,
Yeah, actually, you have, but it's not in the K-map. You've learned this in truth table.
K-map, I know, doctor. Yeah.
Yeah. You've learned how to do the entered variable in truth table, but not in K-map. So here I'm going to teach you how to do entered variable in K-map. So just for you to recall, remember in the first year, you have a truth table, okay, with, for example, 16 lines. 16 lines truth table. And then you will take the value of D, change it to 8 lines of truth table. Remember? And you can use value C and D to make 16 lines truth table to change it to 4 lines truth table. So that is on truth table. So in K-map, we have 16 here. We have 16 output of K-map, 16 cell, and we want to change it to 8 cell, okay, by having entered variable inside. So the usual K-map, we have 0, 1, or don't care, right? Now, we want to make D, so if it's 4 variable, so if it's 16 cell, which means it is A, B, C, D. Now we want to have D as the output. So maybe you will see 1, 0, don't care, and then D, and then D prime or D bar. Same goes to here. Remember the 8 lines truth table? You have 1, 0, or maybe don't care, and D, and also D prime. Maybe 1, 1, 1, and then D here, and then D prime here. So, well, we go through this together after this. Maybe you got the idea later, right? So, well, you have learned this previously through the truth table. So today we're going to see this on K-map, right? You have the basic of this, you have the basic of K-map, so it will not be that hard to understand. Hopefully. Okay, excuse me for taking times.
It's okay, Sensei.
All right. Okay. So we want to collapse. We want to collapse two regular ChemApp cells to become one and third variable ChemApp cells. So we want to combine these two into one. So how does this one become zero? Okay. So the input is the value of E, right? The input of is the value of E, and the output of E is inside the ChemApp. Okay, remember the basic of ChemApp? Okay, now whether E is 0 or E is 1, doesn't matter. Okay, the output will be 0. Okay, either E is 0 or either E is 1, the output will be 0. Okay, so we call this, okay, two cells, we combine this to become 0. So this is 0, right? Okay. Okay, I'll go slowly. Okay. Now let's look at this one. Whether E is 0, okay, sorry. Let's rephrase that. When E is 0, the output is 0. When E is 1, the output is 1. So the output, okay, follows value of E. So we can combine these two as E because the output here follows E, right? Okay, let's look at this. When E is 0, the output is 1. When E is 1, the output is 0. So the output here is the complement of E. So we have E prime or E bar. I'm going to use E bar and E prime interchangeably here in this lecture. Hope you understand. So it's E bar or E prime, okay, means the complement of E, right? Okay, so let's look at the next one. Okay, output. Okay, I will write output is complement of E. Okay, or the inverse of E, right? Okay, let's look at the last case here. When E is 0, the output is 1. Okay, when E is 1, the output is 1. It doesn't matter what E is, doesn't matter what input of E, the output will always be 1. So we combine these two cells as 1. Okay, combine these two cells as 1. So this is 1. When it's always 0, it will be 0. When it follows E, it will be E. Okay, when it's the inverse of E, it will be E bar or E prime. When it's always 1, we combine it as 1. All right. No question here? Question? Okay. Let's move on, ya. Silap. Alright. So let's plot the function with min term 5, 7, 10, 13, 14, 15. So this is how we plot the function in 4 variable ChemApp, which is 16 cells. So 5, 7, 10, 13, 14, 15. Remember? Because it's 0, 1, 2, 3. Is it? No, wrong, right? 0, 1, 2 here.
0, 1, 3, 2.
Yeah. Okay. Then 4, 5,
7, 6.
6. And here, next one, right? 8, 9,
11, 10.
11, 10. And here is 12, 13, 15, 14.
15, 14.
Right? So 5, 7, 10, 13, 14, 15. 5, 7, 10, 13, 14, 15. Okay. Remember how we map the min-term value into K-map. All right. Right. So that's the basic of mapping K-map. Right now we want to group. Okay. We want to use D. Okay. We want to use D as the entered variable. When we plot the function A, B, C, D, okay, remember you have to write the dimension in order. Okay, and then A, B, C, D. If you want to decrease 4 variables into 3 variables, so D is one will be the entered variable. Okay, we call this the entered variable or the map entered variable because it's the one who is going to be inside the map together with 1, 0, and don't care. Right. So how do we do this? Okay. So this is actually it's a min term. So here we actually have 0, right? So whatever the value of A, B, C, and D here, okay, these two will always be 0. So we call this f equal to 0. Okay, the function here, the function ABC of this two cell here is 0. Right? Same goes to here. Okay, there's actually 0 inside this two cells. So whatever the value of A, B, C, A, B, and C here, it always be 0. Whatever the function here, okay, it will follows D. Okay, because when A, B, C is 0, 0, 0, okay, F will be following D, which is 0. When when A, B, C, D is 0, 0, 1, 0, 0, okay, the output will follows D. Okay, the output will follows D, and which is 0. This is D, this is D, right? Will follows D, so it's 0. Okay, and then here the output will also follows D, which is 1. So these two cells is equal to D. Let's look at the first half here, okay, because it's the same D value, 0 and 1. Okay, so these two cells also follows D because the output follows D, which is 0, the output follows D, which is 1, so it's equal to D. This one is equal to 0 because it's always 0. Then this one, always 0. This one, it will follows D. Okay, now it's 1, 0. D now is 1, 0. From here to here, it's 1, 0. 1, 0. Follows D. This one, it's always maintain 1. It's always 1. The output is always 1. So this is defined as 1. And this one, it will follows the inverse of D. Okay, D is 1, but the output is 0. D is 0, but the output is 1. So call it D prime or D bar. Okay. So we can collapse these 16 cells K-map into 8 cells, okay, with 3 variable. With 3 variable, so it will be like this. the new sections, the new sectioning. Right. So it will be 0, 1, 0, and this is D. This is also D, and this is also D, and this is 1, and this is 0, and here is D prime. Okay. Okay? Right? Questions? All right. If no questions, I will proceed. So now we have this, right? We have this entered variable K-map. Now, how are we going to loop this type of K-map? Okay. How are we going to loop this type of K-map? Okay. First, pretends all MEV is map entered variable, which is in this case here is the D, the entered variable inside the map. D. Okay. Pretend all these are 0, loop 1, and read the map as usual. And then first, you just loop 1, and then loop loop MEV, which is D and 1, but you treat 1 as the don't care. Okay? And when you map, D and D bar is different, right? So means first you map 1, and then you map the mix of D and 1 and D bar, D prime and 1. You cannot mix D and D bar. It's D and 1 or D bar and 1. Okay? You treat D and D bar as different. Right? Okay, and then find the most essential prime, where all the MEV must be covered. All MEV must be covered. Right? So let's see the example here. It's already loop here, so I'm just going to draw another one so that you can see. So we have 1, D, 1, D bar. Right? Okay, so first we loop D. We loop 1. We loop 1. Right? So this is A is 0. Okay. B is changing. So we're not going to have that. And then C is 0. So the mean term, because we are looping 1, the mean term is A prime, C prime. Okay. Next, let's choose another color. We're going to loop either D and 1 or D bar and 1. Right? So we loop this one first. D and 1. Right? Okay. So what will the mean term be? So usually, someone want to answer? Anas?
A bar.
A bar.
Yeah. For the yellow one.
Yeah. The yellow one, A bar. Okay, usually when all is 1 here, we call this A bar because A is always 0. Okay? But with nth variable, which is the D, okay, we will also put D in the midterm. So it will be A bar D. A bar D. Okay? This is new to you, right? So A bar D when we loop with the nth variable D. Okay? And last one, let's use the green one. We loop this one. Now we are looping D bar and 1 here. And this is A is changing. It's B is always 1 and C is always 0. So it's B, C bar or C prime, and then D bar. Okay, so it's a sum of product. It's a sum of product. So we can plus here. All right, so this is your sum of product for this. For this. Okay, so this one is just that we want to check for checking. Okay, for checking. Okay. Remember, D plus D bar is equal to 1. D plus D bar is equal to 1. So we can check. Okay. Let's say this is D plus D bar. Let's just try to make another one for you. And we look together. Oops. One, D plus D bar, bar. All right, so first we loop D. Okay, so sorry. Okay, my mistake. First we loop 1. Okay, firstly loop 1. So we loop 1 here. This is 1. Okay, this is 1. Okay, this cell is D plus D bar. That is equal to 1. So we loop this and this together. That's looping 1. And then we loop. So that is A bar C bar, right? And then we loop nth variable D with 1. And we can treat 1 when we loop nth variable, we treat 1 as don't care. So if it gives the benefits to make the loop bigger, we can use 1. If it doesn't give benefit to make the loop bigger, then we can ignore the 1. We just loop the D. Right? Okay. So next one, loop D bar. So this example here is just for checking. Don't worry. It's the same thing eventually, right? So it's A bar C bar, A bar D, and B C bar D bar. Right. I will give you exercise later so that you can check and we can discuss. Since I always start class at 8:30, we don't really have time to do exercise in class. So that is one thing that I want to ask you. So do you want to start class at 8 and do exercise together, or you want to start class at 8:30 and I just give you the questions and we discuss it later? Maybe I will explain to you through video the answer of the exercise, or we can discuss it in the WhatsApp group.
I think it's best if you make a poll.
Poll. All right. Poll, Poll for who wants to be a nerd and start class at 8, right? No, just kidding. Okay. Let's make a poll later.
I get it. I get it.
All right. All right. Okay. So that is all about the entered KMAP. So that's
Yeah,
all about
Absolutely,
the
doctor.
entered.
Doctor.
Oh, questions. Okay.
Yeah, if we had like
Mm.
the one in cell 4, for example, like can we choose cells that are only D, or there has to be a mix of D's and 1?
That is what I mean by when you looping D or D bar, you treat the one as don't care. If it gives you benefits, which means if it will make your loop bigger, so it's better, right? So you can minimize the min term, then you can loop together with one. If not, you can ignore the one. You can just loop with D.
Yeah, all right.
Okay?
Yeah.
Okay, clear? Okay, another questions?
Yes.
Anas?
So you say that we can treat D as don't care, right?
We treat one as don't care. When we loop D or D bar, we treat one as don't care. Okay, we must loop all D, okay? But we can use one together with D to make the loop bigger. Because the bigger of the loop is the better. Understand?
Yeah, but D has the same concept of don't care.
No, one has the same concept as don't care.
One is one.
This one? One. Okay, when you loop D and one together. See my pen? Yes. Okay. When you loop D and one together, so this is D, right? This is one. Okay. You treat one here as don't care. Okay. So you can just loop these two, D and D. But if you loop it together with one, it will make your loop bigger. So we loop it together with the don't care. Sorry, with one, which is treated as don't care.
Okay.
Okay.
Thank you.
All right. Any more questions regarding the entered KMAP? Before you proceed, right? Maybe you are still in a blurry right now. You can ask later. All right. So proceed. Okay. The next one is the transformation is just telling you what's the transistor looks like inside the gates. I am sure you have learned this in electrical device. And then bubbles, the De Morgan formula, and how to make non-only circuit. I have a video on this. I'm not sure if you realize or not, but the video is the second video that I made when I start YouTube videos. So it's quite it's easy to understand, but the video graphic is really bad. I'm not sure if you can see right now. I'm opening my YouTube. Can you see it, or am I just sharing my slides?
No, only the slides.
Oh, only the slides. All right, okay, later. You can just check the video about SOP to 2 input NAND and POS to 2 input OR. It's about how to do this. How to do this from SOP to NAND and POS to NOR only. Okay. Okay. And then power consumptions. It's about the power consumed by the TTL and CMOS and how to calculate it. That's it. And then propagation delay, right? Propagation delay is well, a delay. Every circuit has a delay when it go through a gate, right? When it go through a gate or something. So the delay is calculated as the propagation delay is calculated as T propagation from high to low plus the time of the propagation from low to high, okay, added, divide by 2. So we are actually finding the average, okay, average of these. So what is the TPLH? Okay, it is, you always, like in the exam, right, you always given this picture, right? This picture. There's an input and then there's an output, and then maybe there is no symbol of this, no this. It just says here is 50%. And then find the TPLH and find the TPHL. So you already know HL mean high low, LH means low high. But which one is it? Is it high low here or high low here? Or is it low high here or low high here? So some students have confused this from my previous class. So just remember, it's about the output. The output change. Okay. The output change. So not about the input, it's about the output. So this is the TPLH and this is the TPHL. And we find it from the 50%. Okay, from the 50%. And we want to find the average, which means if the TPLH is steep and the TPHL is, what is the antonym of steep? Not steep. So you will still get the average of this. So the average of these two is the propagation delay. Doesn't matter. It's not that hard to understand. It's just that we just want to find the delay when changing from low to high and high to low, and then find the average, and that will be the propagation delay of this output. Next, critical path. So in a circuit like this, we have multiple paths. So let's see. This is the first path, okay, A, and then going to XOR and E. So that's the first pass. And there also B, oh no, A going to AND gate and become D going to XOR. And another one, B going to an inverter, become C, and then going into AND, become D, and going to XOR, become E. So there are 3 paths here. Okay. So the first path, okay, we can calculate the delay, which is when the the electrons is going through the gate, right? So it is defined here that the inverter has delay, the delay variable as tau. So we call this tau, right? Tau. I'm not sure how the pronunciation in English, but I do learn this as tau in Japanese. I think it's the same. Tau. Okay?
Yes, it's the same.
Ah, it's the same. Great. Okay. So it's tau, okay? So the inverter is tau, the AND is tau, and the XOR is 2 tau. Okay, the XOR probably has a longer delay. Okay, so we can calculate the delay. So the first pass, which is the pass of A and then E, is just 2 tau because we're just going through this, right? And then the pass of A, D, E, which means this one, A going through AND and going through XOR is 3 tau because it's tau from AND plus 2 tau from the XOR. So it's 3 tau. And then the last one, where B becomes C, become D, and become E, okay, is 4 tau because it's tau, okay, this one, tau, the inverter, plus another tau from the AND and from the XOR, which is 2 tau. So we have 4 tau. 4 tau, right? Okay. So the longest delay is called the critical path. Critical path. Okay, remember, when we design a circuit, okay, we want the best performance. Okay? And the best performance is by looking at the power consumption and area, which we're not going to discuss, and also timing. Okay, so this delay will cause bad timing. Okay? Bad timing. So we want to know which path has the most critical delay. Okay, which means we can reroute the circuit. We probably can reroute the circuit if the circuit is more complicated. Like we can reroute it to make it less critical. So in not debugging, in verifying the circuit. So when you design a circuit, so you will work in a team, right? So one person will design the circuit, and then one person will do the checking, like the analysis of the circuit. Okay, the analysis of the circuit, and if there is a lot of critical paths, and the analysis, the timing analysis engineer will send it back to the designer. Your design is bad. Change this path, this path, this path because it's critical. So the designer has to do it again, and then when the designer has done design it again, it will give the design to the circuit analysis. Okay, and circuit analysis will analysis the timing again, the power consumption again, and return it back if there's still a problem with the critical path and too much power consumption, and if the area is too big, so it will give it to back. So it's like go here again, yeah, back and forth. So what I want to say is the design process is not easy. It's not one way. Okay? It will come back to you. If you, as a circuit designer, if you do the design last minute, it will come back to you. Okay? So that's just not related to this class anyway. Okay, so this is the survey, is it? This is the delay for each gate as of, I think, 2014, maybe, when the slide is made. Maybe the number here should have been decreased since the technology have been improved. Okay, the transistor technology. Oh, bye Sam. Okay. So that is about the propagation delay and the critical path. Now, we're going into the hazards. Okay, we're going to the hazards. So, hazards is caused by the propagation delay. So, hazards. So, what is a hazard? Hazard is a characteristic of digital circuit. So that we can say that digital circuit, that IC, has a hazard. Okay. So hazard is a characteristic of the digital circuits that caused by the propagation delay, of course. But the phenomenon, the hazard phenomenon, is called the glitch. The glitch. Glitch is the phenomenon. Has any of you have ever experienced glitch before in your life? Or knowing any story about glitch before? You know what glitch is?
Rocky Rough.
What dia? Okay. What is it?
Macam dalam cerita Wreck-It Ralph.
Oh,
Ada
macam
glitch.
dalam cerita ada glitch. Okay. Macam dalam cerita tu. Saya tak tengok. Sorry. Okay. I didn't watch the movie. So, yeah. So, you might have been familiar with the glitch, right? But we're not talking about the real world glitch. Here we are talking about the circuit. It's a sudden malfunction. Wow, what was just happened right now? Kind of things, right? Okay. So it's an unwanted transition, right? So yeah. I have this one story that's not happening to me. It's just the story that I read on Reddit. It's a story that I read on Reddit. It's about a husband and wife, right? A husband and wife. They are together going down the stairs, right? While talking. And then when they are on the last step of the stairs, the wife says, on the split second, the husband is suddenly not on her side. And when he tried to look for her husband, the husband is back on the top stairs, on the top of the stairs. So it's like unwanted transition. So that's like her experience of the glitch in the real world. I haven't experienced any of that. I don't even believe in that. Okay, it's an unwanted transition. So that's a glitch. It's a phenomenon. And in the circuit, this phenomenon is called hazard. Okay? And it happens when an input changes state and the signal takes two or more paths through the circuit, and one path has a longer delay than other. Don't worry about that. It's just a sentence. Okay, I'll explain it to you later. Okay. So the hazard is related to glitch is actually the characteristic of the circuits due to the glitch phenomenon. Okay. A hazard may produce a glitch. Okay. This glitch phenomenon might be caused by the hazards. You can think it the other way around. You can say that there's a glitch, so this circuit has a hazard, or the characteristic of the circuit itself, which is a hazard characteristic, can cause the glitch. Okay, can cause the glitch. So there are two types of hazards, which is the static hazards and the dynamic hazards. So the static hazards, since we have two values, okay, which is 0 and 1. So our static hazards has also two types of static hazard, which is static 0 hazards and static 1 hazards. So static 0 hazards means when the value is static at 0, so this is 0. When the value is static, and this is 1, value is static at 0, there's a glitch, which is the unwanted pulse. And it backs to normal. So this is static 0 hazards. For static 1 hazards, mean the value is supposed to be static at 1, and then there's a glitch where it goes to zeros. 0 pulse. And go back to 1. Right. And dynamic hazards, when a single input variable change causes not a single change at the output, but multiple changes before settling at the new value. It means, okay, you have multiple pulse, multiple hazards. That's the dynamic hazards. All right. So this is the example that is in a better figure. Okay, now let's see a circuit with a static hazard. With static hazards. So we have a circuit A plus A bar here. F is equal to A plus A bar. So this circuit will always be 1. Will be always be 1. Because an OR, right? So OR unless both are 0, it will always be 1. Okay. Unless both input are 0. But now the input is complement each other. So it's either it's either 0, 1 or 1, 0. So means the output will always be 1 because the input is complement each other. When A is 0, A prime must be 1 because it's the same, right? It's just inverse. When A is 1, A prime must be 0. Complement each other. All right, I know you understand that. So now, let's see. Here, where's the glitch? Here's the glitch. Glitch. So, this circuit, the characteristic of this circuit, it has hazard. Has hazard. Okay. Due to the delay inside here. Due to the delay inside here. Okay. While A can straightly go to the OR, okay, A prime need to go through the inverter. And the delay from the inverter, the propagation delay from the inverter will cause some delay here, right? So there's delay here. Okay. So this delay will make a small period here where both input is 0, which means the output will become 0. the output will become 0 here. So this propagation delay here will cause both input to be 0 at the same time, which will cause the glitch. Therefore, this circuit has hazard. Okay? Has a hazard characteristic. Understand? This is just a simple circuit. And what is this? Right? You asking me, what is this? Can anyone tell me what is this?
A
I can
static one
understand.
hazard.
I know. I'm asking what is this time delay?
Critical path delay.
So if you know the what is timing diagram, right? So usually you draw the output. You do like this first. So you want to know where do you want to change. So 1, 1, 0, 1 plus 0, 1 or 0. Got that. 1 plus 0 is 1 here. And then, 0, 0. So the glitch should be here. And then 0, 1. So the glitch should be here. But why is it here? Not here. So what is this time delay?
Is that the propagation delay?
From
F- from low to high to low. I mean low to high.
low to high?
Yeah, is this the propagation delay?
It is. It is a
Oh,
propagation
oh.
delay. Of? Is it tau?
Oh, from the
Is it
input to the output. Okay.
is it T? Is it this one?
Yes. It's from the not gate.
No, it's from this one.
I see. Okay.
Right. Because this is F, right? So both A and A bar is going through the XOR. So it's actually the combination of this and this. So it's T plus another maybe T1 here. So this is T plus another one. From the input here to here. T plus T1, for example. T1. Right? So that's why we don't have the glitch here. We have a delay and then we have a glitch here. Because we have the propagation delay here and also here. Okay, so this is only 2 gates. So when you have more gates, you have more propagation delay. So is hazard a good characteristic or a bad characteristic? Is it do we need to improve this circuit or not?
I believe so. Yes.
Yeah, yeah. Can anyone else tell me why is that? Why is it a bad thing? Why is hazard a bad thing?
Because sometimes it give us an unwanted output.
Unwanted output? Correct.
Yeah.
Correct. But well, if it's not broken, you don't have to repair it, right? So that's like our motto of life. No, it's not. So you've heard that, right? When it's not broken, you don't have to spend time to repair the situation. So is it always with hazard? Is it you always have to repair the circuit? You always have to improve the circuit.
Won't you get an inaccurate output if you don't repair it?
Yes, we will get not accurate output if we did not repair it, but not in all circuits. Remember, we have synchronous and asynchronous circuit. Sorry about the almost end of class writings. Okay, we have synchronous and asynchronous circuits. With a synchronous circuit, the output will follow the clock, right? The output will follow the clock. So this is the clock, right? And the output will only read at the falling edge, for example. So if the glitch happened here, doesn't matter because we're not going to read the output. The important data is here. We only read this data. Okay. So if the output, if the glitch happened here again, it doesn't matter. Because what's important is the timing here. We only read the data at the falling edge. That's the synchronous, right? Synchronous. So in synchronous circuit, okay, hazard is not a critical problem. Get that? But for asynchronous, it will be a problem because the output will change according, not according to the clock, according to probably the input. We follow the input, not follow the clock, for example. So all the data is important all time. So this will be the unwanted data, the glitch. You understand what I'm saying? Questions?
Yeah, yes, sir.
Okay. Thank you. Okay. Now, how can we eliminate the hazards? Is one way to do it is to insert another delay to the circuit. Another way to do it is to reclock the final output signals. And the third way to do it is to insert a redundant term. Okay. In the form of an additional gate. So insert another delay to the circuit. Maybe we can add a buffer here. And the buffer also has a propagation delay T, probably. Same with this inverter. Then A and A prime or A bar here will go into the OR gate at the same time. But this is hard to do physically because we don't want to insert an inverter. We can just insert a buffer because, you know, when you go through a buffer, it's just the same thing. 1 will be 1, 0 will be 0, right? But it is physically hard to design a buffer with a certain with the propagation delay because of the characteristic of the transistor and everything. It's hard to design a buffer with the same propagation delay with any clock, right? Maybe you if the buffer is half T, maybe you can add 2 buffer here, right? But adding buffer means you adding gates, mean you add area to the circuit. Then the performance will be off. It will be like a trade-off. Okay, you want to eliminate the hazards? Sure, fine. Get this additional area. Then your area performance will be down. All right. So But if it's a serious problem, like in the asynchronous circuit, you have to take the trade-off lah, of getting a bigger area. All right. Record the final output signal. I'm not going to explain it here because we're not talking about the clock here. And insert a redundant term in the form of additional gate lah. Yeah, we're going to see this but with a different circuit. Okay, so this is another circuit. This is another circuit which is multiplexer, 2-to-1 multiplexer. A, B, S, and then 1. Okay, 2-to-1 multiplexer. Okay. Okay, let's say A here is 0, B is 1. Right? When S is 0, okay, F is equal to A. When S is 1, F is equal to B. Right? So the circuit inside this multiplexer box here is looking like this. Okay. So when we give, for example, see this example here. Okay, not sure if kind. Okay. Let's just look this first half here. Okay, you don't have to care about this one. Right. This is when hold on. Let me recall this. I think S is 1, B is 1, and A is 1. S is 1, B is 1, and A is 1. Here, this side. Okay. Don't have to care about this first. So when A is 1, B is 1, and S is 1, so here S bar will become 0. And since 1 and 0, this is 0. And this 1. Right? 1, 1, 1, 1, 0, 0 here. And 0 plus 1 is 1. So F here is equal to SB. And since S is 1, F is B. So actually in the circuit here, it will follow SB. Okay. So S is 1. Since S is 1, SB is 1. And S prime A will be 0 here. So the F will be 1. All right, get the circuit there, right? Okay. Okay. So this is the 2-to-1 multiplexer. And then when we change S to 0, S now is 0. So this is supposed to be 0. And this is 1. And this is 1. Right? Now the F will follow S bar A. Right? Okay. When S is changing to 0 here, S will be 1. S prime will be 1 because it has inverter here, but with some delay. So due to that, SA will also have delay. Okay, it's a longer delay because it's a delay for the inverter and the AND. SA will turn to 1, but with a delay. And SB will be 0, but with a delay of delay from the end, right? From the end. And due to that, there are times where F will glitch to 0. Why? Why? Can anyone answer why?
Can you repeat that again? The question. Can you repeat
Kenapa?
again the question?
Sorry, Anas, I couldn't hear you clearly.
Can you repeat again the question?
Oh, okay. Why do we have a glitch? F turns to 0 here. Why? Okay, to get that,
Because S changed to 0.
because S is changed to 0, and then
So the output will be S bar A.
so our Anas.
So the output will be S bar A.
So output B is bar A.
Yeah.
So output will be S bar A. S bar A is 1. This is S bar A. Yeah. This is when it is equal to S bar A. This is when it is equal to SB. What is this?
Excuse me, doctor. Is it the delay in the inverter? Propagation delay.
Converter? There's a delay. Yes, there's a delay, and then okay, what is the mean term here? What
There
is the
is
mean term?
when SP is going from high to low, and S bar A is going from low to high. There is a delay there, and those two delays give you moment
Yes.
is 0 0, and then you get the delay.
So what is this value? This is equal to what? So this part is equal to SB. This one is equal to S bar A, and this one, the glitch here, is equal to.
The glitch is 0. Two AND gates will produce 0, and
know.
it's 0.
I know it's 0, but what is the mean term here?
The meter will be
Is it SB? Is it SA? Is it S bar A? Is
AB.
AB? Okay, we have AB. And then other? Others? Right. No answer? So AB is incorrect, but thank you for trying. Okay, to know that, we need to remember what is F. F is equal to? We have,
S bar A plus SB.
yes, S bar A plus SB. And what would make this 0 again? So this is OR, remember? OR 0 0 0 1 1 0 1 1 0 1 1 1. So it will only goes to 0 when both input of the OR is 0. So here S bar A is 0, SB is also 0. Means okay, there are some period of time where both S, B, and SA is 0 at the same time. Okay? 0 at the same time. Okay, so that will cause the glitch here. So here the value is S prime A plus SB. It follows S prime A plus SB. So this is also S plus A plus SB, right? This is S plus A plus SB, but SB is 0. So it's SA plus SB. This is 1, right? There's a value. So it will become S prime A. Same goes to this. This is S prime A plus SB. But SA is 0. Remember the purple one? So, SB, which is 1. This one, which is 0. So we got our sum of product here. So sum of product of F is S plus A plus B. So how can we eliminate this? By adding some redundant path to it, right? So let's see. We know that FB is SB plus S prime A. So we map this into K-map. And then we find SB and S prime A, right? So when you draw this K-map, it will be SAB. SAB. Okay, the 2 to 1 multiplexer K-map, right? So, to find the glitch is in here. Oh, it's not written here. But it's written in the textbook. So, here, if any two adjacent means neighboring. How do you spell adjacent? Adjacent. 1. When you find two neighboring 1 that are not in the same loop, okay, that are not in the same loop, okay, then that is the static 1 hazard. So we have to loop the two adjacent of 1. We have to loop the two adjacent of 1 and add a redundant. Okay, we don't need this, but to eliminate the hazards, okay, we have to add this to our circuit. So this is AB. So we add the term here, the min term here. So our circuit to eliminate the hazards will be like this. So we have the additional AB path, AB gate here, AB circuit into our OR gate. Get it. Now F is S prime A plus SB plus AB, right? So this is how we eliminate the hazard. All right. If the question asks for the sorry. If the Muhammad Al Sayed is asking if the question asks for the minimum term, do we add the additional term to avoid the hazard? If the question asks for the minimum term, oh no, if the question is asking find the minimum term, then you just give them this answer, the minimum term. We don't care about the hazard. But if the question is asking how can you eliminate a hazard from this term, this minimum term, then you will have to add the redundant term?
If the hazard was 0, do we handle it differently?
Oh, if the
I mean, if
hazard
it was
is
1, yeah,
if
instead
the
of 0.
hazard is 0, it will be max term, not min term. So it's the inverse of what we are doing now is the static 0 hazard. Same goes to this circuit just now. Okay, it doesn't look like a circuit anymore. Okay. This is, okay, we call this an AND/OR circuit. Okay. For AND/OR circuit, you will get a a static 1 hazard. Okay. AND/OR circuit type of circuit, you will get a static 1 hazard. If this is AND, you will get a static OR, because the truth table here, the default is 0 unless both is 1. So you get a static 0. So the hazard will be when when there's a period of time where both input is 1 at the same time. So that will be the static 0 hazard when this is AND here. So when we're talking about the min term or the max term, you have to add another max term for the static 0 hazard. You just have to, change your thoughts about this, okay, to the max term. So we only do the min term because it's easier to see, right? So I'll find example on the static 0 later. So this is only example for min term, right? Static 1 hazard. There's no example for the static 0 hazard. I'll find it and probably try to create it, maybe using the simple circuit like this one. It is actually on the textbook end of topic exercises. So yeah, I will try to do that and give it to you later, probably in a video form. All right. So it's 9:54. I think you will have to get ready for the next class. So there is no more question here. But who is this? Mujtaba is asking, why can you send message to everyone? So I didn't block you. You're not blocked. It's just that you have to change the address. When you enter a message on the chat, on top of your typing, there's a column, not like column, like drop down to choose who you want to send the message to. Change it to everyone, and you can send the message to everyone, I think. Okay. Is there any more questions?
So far from me, there's nothing, Sensei.
Okay, I hope it's clear. This is actually just a revision class. So next Sunday we will also do some revision class. You can see the next slides to what we are going to do for the next class, the revision class. Okay, it's quite boring. Next Sunday class will be quite boring. I will try to do a video on chapter 1 to 3 eventually. But I will not rush doing the video. It's for those who are trying to catch up with this class, with the Thursday class, right? I will not rush on the chapter 1 to 3 because you've done this previously in digital electronics. It's just a revision, except for the hazards and probably some of the entered value of the camera, right? Okay, so be nice and help your friends if they ask questions about this class. You are going to be better, understand better when you try to teach the other. Okay, so try to discuss with your friends about today's class, about the hazards. Probably you may try to find out about the static 0 hazards, because we only do example on static 1 hazard, right? Okay, so if there's no more questions, so I would like to end the class for today, because I also need to rush to the next class, right? So have a nice weekend, everyone.
Teacher, is there any attendance?
No, because the Webex will record if you're coming to class today, so I will just take that as attendance.
Oh, okay.
All right.
Thank you, Sensei.
All right.
Thank you, Sensei.
Thank
you, Doctor.
Thank you. Thank
Hello,
you. So,
Tashmasa.
thank
you, Doctor.
Thank you.
Assalamualaikum.
Waalaikumsalam. Thank you.
Thank you, Doctor.
Okay, thank you.